Here is a puzzle that sits at the very heart of interpretability. A layer in a neural network has a fixed number of neurons, yet the world it models has far more useful features than that. So where do all those extra features actually go? Anthropic's toy models of superposition from 2022 gives a surprising answer. The network cheats. It packs in more features than it has dimensions by letting them quietly overlap in the same space. That single trick explains a lot about why these models are so hard to read. Let's unpack what it really means. Now, to feel why this matters, compare two ways a network could store what it knows. The tidy picture is one neuron per feature. Each concept gets its own dedicated direction. So you could read the whole network like a labeled dashboard, just glance at a neuron and know what it means. Clean, interpretable, wonderful. The catch is capacity. You can only ever represent as many features as you have neurons, and for real data, that is nowhere near enough. Superposition throws out the tidy picture. Instead of one neuron per feature, the network stores features as overlapping directions in the same space, sharing neurons between them. It gives up a clean map in exchange for holding far more concepts than its neuron count should allow. Follow the idea through, and you can see exactly why a network would take that trade. Start with the demand side. Real data carries a huge number of potentially useful features, many more than any single layer has neurons to spare. The network simply has more it wants to represent than room to represent it cleanly. Because of that squeeze, it stores those features as overlapping directions that sit nearly at right angles to each other. Packing many almost perpendicular directions into a small space lets a handful of neurons stand in for a much larger set of concepts. This trick is not free. Directions that overlap bleed into one another, so the network accepts a little interference, a bit of crosstalk between features. It tolerates that noise because most features are rare, so they seldom fire at the same time. The visible result is polysemantic neurons. Any single neuron now lights up for several unrelated concepts, because it is shared across many overlapping directions. That is a big reason reading a network by staring at its neurons is so genuinely hard. So let's pin down the three ideas that make superposition tick. More features than neurons. By storing concepts as overlapping directions rather than one clean direction per neuron, the network represents far more than its raw dimension count would ever suggest. It treats its activations as a compressed code, not a neat one feature per neuron map. This works because features are sparse. Most concepts are rare and rarely active at the same moment, so the overlapping directions almost never collide in practice. And that near miss is exactly what lets the whole packing scheme pay off instead of turning into noise. And the cost is interpretability. Overlap produces polysemantic neurons, which is why researchers reach for sparse autoencoders to unfold the tangled, overlapping directions back into separate, individually readable features you can actually name. All right, let's lock in what to remember about superposition. Superposition lets a network store more features than it has neurons, by representing them as overlapping directions in activation space. It works because features are sparse, so the network can pack many nearly perpendicular directions and accept only a little interference between them. The direct consequence is polysemantic neurons, single neurons that fire for several unrelated concepts, which is why interpretability is genuinely hard. That is also why sparse autoencoders exist, to unfold the overlap back into clean, separate features you can read. It reframes a network's activations as a compressed code rather than a neat map. Want more AI concepts explain this plainly? That is exactly what we do over at Standarity.com.